Hello everyone, and welcome back. Last time we continued to look at the magnetic field and magnetic forces, and in particular we looked at the magnetic forces that acted on currents in wires, and then we looked at what would happen if we had a loop in a magnetic field and that loop was not aligned to the magnetic field, and we found that it created torques on the loop. What we're going to do is we're going to continue looking at magnetic forces today, but we're going to take a slightly different approach. This brings us to section 22, entitled Electromagnetic Induction. And what I want to do is start out with a little mental experiment, a Gedanken experiment, as Einstein would call them, and then we'll take a look at a demonstration and see what happens. Let's imagine that we have a magnet here. Let's look at the north pole of the magnet. So we've got the magnetic field lines coming out of the north pole. And let's imagine that we take a wire and make a little round loop. So I have a little round loop of wire. And I'm going to take this loop and I'm going to put it in the magnetic field. And then I'm going to move it toward the magnet. So I've got a loop of wire and I'm going to move this wire toward the magnet. Well, let's think about that. This wire has charges in it. There's no current in it at the moment, but there are charges. There are positive and negative charges in the atoms that make up the wire, the material of the wire, the copper in the wire in particular. Let's think about the motion of the positive charges. As I move the wire, those positive charges are actually moving, so they're moving in this direction in the magnetic field. Well, we've got moving charges in a magnetic field. Maybe there are forces on those charges. Well, let's think about what those forces would be. Let's imagine we're looking at this situation from this direction. So we've got a loop of wire that's moving away from us and a magnetic field that looks like this. Well, let me draw that. So here's our loop of wire. And let's imagine we're looking at it as it moves away. So the velocity is into the board. It's moving away from us. What about the magnetic field? Well, let's take a point, say, at the top of the loop. So here's our loop. Let's take a look at the magnetic field at the top of our loop. It's kind of pointing this way. So in our picture, it's pointing towards us and upward. Let's break that down into two parts. I'm going to take this magnetic field and draw the part that's pointing toward us and upward. Now, if we think about the part of the magnetic field that's pointing toward us, we've got a velocity that's this way and a magnetic field that's this way. So a velocity that's this way, a magnetic field that's this way. What force is that going to create on the wire? On the positive charges in the wire? Well, the angle between V and B is how much? 180 degrees. Sine of 180 is 0. So there's no force. The part of the magnetic field that's pointing toward us, with the loop going this way, that component of the magnetic field will create no force. But what about this part? Well, let's draw that in. We've got then the magnetic field that's in that direction. We've got a positive charge that's moving away from us, as I've drawn over here, into the board. The magnetic field is pointing up. It's a positive charge. Positive charge. What force is going to be exerted on that charge? Well, we know the magnitude will be F equals Q VB sine theta, magnitude Q VB sine theta. What about the direction of the force? How do we figure that out? Right-hand rule. Try the right-hand rule, see what you get. Think about it for a second. Let's do it together. V is into the board. B is up. The force is to the right. So the force, in this case, will be to the right. There we go. Let's look at another point on our loop. Let me draw in our loop over here. So here's our loop. What about the magnetic field that's down here? That's going to have a component, again, that's toward us, but at this point it will be pointing downward. Well, again, we know the component that's pointing toward us. Let me just remind us, and I'll draw in our eye. So that's our eye, looking this way at the loop as it's moving away from our eye. Here we have a magnetic field that's pointing downward. So let me draw that magnetic field. So down at a point at the bottom of the loop, we have a magnetic field pointing downward. What direction is the force going to be on the positive charge in this case? Well, V is, again, into the page, into the board. B is downward. The force is to the left. Draw that in green again. The force is to the left. So that's the force. That's the force. Well, what about a point, let's say, over here? What about a positive charge over there? That would be over on the right side of our loop, over on this point of the loop over here. In that case, the magnetic field is going to be pointing to the right. So over on this side, again, toward our eye and in that direction. The part toward our eye is not going to contribute any part to the force. So over here we'll have a magnetic field in that direction. What's the direction of the force in this case? V, B, the force is downward. And what about over at this edge of the loop, on this side of the loop, over here on the left side, the magnetic field will be pointing to the left. And again, we have a magnetic field pointing this way on our charge. This way, what's the direction of the force? We have V, B, this way. Whoop. Hope you don't see that. V, B, the force is upward. There we go. We have forces acting on the positive charges in a clockwise direction, always around the loop. What if we were to look on at the forces on the negative charges? Well, you can figure that out. The forces on the negative charges will be in exactly the opposite direction, in a counterclockwise direction. But positive charges moving clockwise corresponds to a current that's clockwise. Negative charges moving counterclockwise corresponds to a current that is clockwise. So it doesn't matter if we look at the forces on the positive or negative charges, both of them are going to give rise to a current in the clockwise direction. So moving this loop in the magnetic field creates a force that will make a current in the loop. It will create a current in the loop. Well, that's very interesting. That's not completely surprising. It follows exactly what we were just thinking about in terms of our forces last time, forces on currents. So that makes sense. Well, let's actually see if we can demonstrate it. Let's give it a try. Here I have a galvanometer, which is a very, very sensitive ammeter. It measures current. And here I have a magnet, and what I'm going to do is take this wire and make a loop, and I'm going to move that loop toward the magnet. And we'll see if we actually get a current by watching this needle here. So I'm going to move the loop, I'm going to hold the magnet still and move the loop toward the magnet. And there we go. Whoops, I missed the magnet. There we go. We actually see there is a very slight movement of the needle, meaning we have a very, very small current. Well, that's maybe not very impressive. How could we get more current? Well, one idea is, what if we, rather than take one loop, what if we take two loops? So I'll make two loops here, and we'll do the same thing. So I'll move two loops, and notice we get a little bit more current. Well, perhaps what if we had more loops? Here, I've got a whole bunch of loops. These wires, basically, one wire comes in here, goes around and around and around and around many times, actually 1,000 times, n equals 1,000. So maybe we get more current if we used this. Well, let's try that. I'll plug this in here and connect the other end of the wire over here. And now, again, I will hold the magnet still and move the loops toward the magnet. Let's see what happens. Well, look at that. We get a whole lot more current. Now, let's notice a couple things. First, we get a different current, a different direction. The needle going one way tells us the current is in one direction. The needle going the other way tells us the current is the other direction. We get a current in one direction when I move the loop toward the magnet, and in the other direction when I move the loop away from the magnet. Whoop. Also notice we only get current when the loop is moving. So if I move the loop, it's only giving us current when the loop is moving. If I just let that stand still and don't move it, we get zero current. So we only get current when the loop moves. Now also notice the amount of current we get depends on the speed of the loop. So if I move the loop slowly, we get less current. Slowly back, we get a little current. But if I move it quickly, we get more current. Well, very, very interesting. Well, there we go. We do see a current created in the loop. Excellent. Not completely surprising. It goes along exactly with what we talked about last time. But let's change this just a little bit. Let me redraw what we were just doing here. Here was our situation. We have our loop, well, it's a much bigger loop here in the picture. We have our loop, and we move our loop through the magnetic field. And what do we find? We find a current in the loop. Excellent. Not completely surprising. Let's try something a little bit different. Rather than moving the loop toward the magnet, toward the magnetic field, what if we move the magnet? We keep the situation exactly the same, except now, rather than, this would be my magnet, rather than moving the current, the loop, toward the magnet, we move the magnet toward the loop. Well, what's the difference? The difference is that we now do not have moving charges. The charges are stationary. Will we get a current or not? All we're going to do is, rather than moving the loop toward the magnet, we're going to move the magnet toward the loop. But now the charges are stationary. Will we get a current or not? Well, that's a very good question. According to our force equals QVB sine theta rule, we would expect not to get a current. Well, let's give it a try and see what happens. So let's try the same thing, but now, rather than moving the loops, I'll move the magnet. Well, what do you think is going to happen? Let's see. Up. We also get current. And again, if I move the magnet slowly, a little current. If I move the magnet back slowly, a little current in the other way. But if I move the magnet fast, more current. What if I switch the magnet around? If I put this end in, I get current to the right. But if I put this end in, I get current to the left. Well, that was a bit of a surprise. We have got a new magnetic force going on here. Where is this coming from? Well, this is actually what we call electromagnetic induction. That somehow the changing magnetic field creates an electric field that is pushing those charges around the loop, so to speak. That's where we get this term electromagnetic. We're not talking about just magnetism or just electricity. It's a combination of electromagnetism. They're joining together somehow. This result actually contradicts Kirchhoff's loop rule. Remember, the loop rule said that if you go around a closed loop, the total changes, the sum of all of the changes in the potential have to equal 0. Well, in this case, it seems like we're going around a loop and we are getting an increase in voltage all the way around the loop that's pushing those charges around. Well, what's going on here? To understand this idea, we need to introduce a new concept, a new quantity. It's called the flux. Let's take a look at it. To understand flux, and in particular magnetic flux, I want to use an analogy. And I'm going to talk about water flux. Let's imagine that we have a stream or a river, something like this. So here's the ground, and here's some water in the river that's flowing this way. And we're looking at it from the side. So this is the top of the river going down, deeper into the river, down to the ground level. Up the top, the water is flowing very rapidly, but as we go down, because the water is dragging against the ground, it slows down. So we've got a high velocity up here, and these are the velocities of the water at different points. High velocity up here that decreases as we go down. Let's imagine we have a little fishnet. So a fishnet, basically like a little loop, and at the back of the loop, we've got like the gauzy part of the bag back here. So here we've got our loop, we've got a handle with the gauzy part of the bag. And I'm going to put the loop down into the water. So imagine we take our loop and we lower it down into the water like this. So there we go, there's our loop, and there. Okay, so there's our net. And what I want to think about is the amount of water flowing into the net. How much water flows into the net? Well, what will determine the amount of water that goes into the net? What quantities will determine how much water flows in the net? Well, how big the net is, how big the opening of the net. If we have a very small opening, we'll get a little bit of water. If we have a much larger opening, we'll get more water. So the area of the opening, the area of this opening, will affect how much water we get. So the amount of water will be proportional to the area, the opening area of our net. What else? Well, where we put the loop will affect how much water goes into it. If we hold the loop near the top, where the velocity is very high, we'll get a lot of water. If we hold the loop down here, where the velocity is very small, we'll get much less water. So what's going to determine what will affect it? The velocity of the water. So the velocity of the water, or the speed of the water, will affect how much water goes through the net. What else? There's actually one more thing. What about how we hold the net? If we hold the net like this, so that the opening is open and the water is able to go right directly into the loop, like this, we'll get a lot of water. But if we hold it sideways, then the water will go right past the loop and not be going into the opening. And then let's just imagine if we could actually take our net and turn it backwards, we'd be getting water coming out of our net rather than going into our net. So let's imagine we actually have two possibilities. Now, most fish nets will actually reverse and just flop through the other way, so that doesn't matter. But let's imagine that for our loop, like the loop we used last time, that our loop has a particular direction, a particular normal line. Actually, we'll use that to also talk about the direction of the area of our loop. I'll say that my loop has an area that points this way, which is in the normal line direction, rather than this way. So the area of our loop, we'll say, points in the direction of the normal line. So we can have a positive amount of water going into our loop if it's in the same direction as our area, or we might have a negative amount of water coming out of our loop, so to speak, if our area pointed the opposite direction. So we can think of our area as pointing the direction where our net is actually pointing. If we have the water going into our net, we have a positive amount of water. If we turn it around and it goes the other way, we'll have a negative amount. So the angle between our loop and the water vector, the velocity vector, will determine how much water goes into the loop. Well, let's think about this. When the area vector is in the same direction as the velocity, in other words, when the angle between them is 0, we get a maximum amount of water. When the angle between them is 90 degrees, we get 0 water. And when the angle between them is 180 degrees, we get negative amount of water, so to speak. Well, what trigonometric function does that sound like? Let me just write this down. So for 0 degrees, we get lots of water. For 90 degrees, we get 0 water. For 180 degrees, we get negative lots of water. So positive, 0, negative. For 0 degrees, 90 degrees, 180 degrees. What does that sound like? Does that make you think of any particular trigonometric function? Well, cosine. That's the cosine of the angle between the area vector and the velocity vector. So we will then write that this depends on the cosine of theta, where we've got to make sure we keep in mind, what does theta mean? Theta is the angle between the area vector and the velocity vector. Excellent. Well, as it turns out, that's all it depends on. That's all that this amount of water that goes into our net depends on. This quantity is what we will refer to as the flux. The flux of water, the amount of water going into the net. The symbol that we'll use for flux is a capital Greek letter phi. A phi looks like a capital I with a circle around the middle. So that's the capital Greek letter phi. Lowercase phi we have seen before, and we've used that for angles before. So here is the flux. And we will write that the flux is equal to the speed, v, times the area, A, times cos theta, where, let's remember, theta is the angle between the velocity vector and the area vector. And this we might think of as the water flux. There we go. So this is very straightforward. Just, it's a measure of how much water is going through the loop, through the net in this case. Well, this is the same idea that we can use for any kind of vector field. Any kind of vector that forms a field that has different values at different points, we can define a flux for that field. In this case, we want to talk about the magnetic flux. So what would the magnetic flux be equal to?